Okay, in this video here, I'm going to show you how to use mathematical induction to prove something. When I see you in class, we'll talk about why it's true. So here's how it works. Let P of n be a statement about a positive integer n. Suppose that P of n is true when n equals 1. This is sometimes called the base case or the anchor case. Also suppose that P of n is true for n equals k plus 1 whenever it's true for n equals k. Then P of n is true for all positive integers n. So this is the principle of mathematical induction, and these are the things that we have to show in order to use this method of proof. Okay, so let me show you some examples now. Okay, now let P of n be the statement that 1 plus 2 plus 3, so the sum of all the numbers stopping at n, is equal to n times n plus 1 over 2. Let's take a look at what this is saying for some specific values. So if we look at 1 plus 2 plus 3, this statement is saying that it's equal to 3 times 3 plus 1 divided by 2, which is equal to 3 times 4 divided by 2, which is equal to 6. And we can see that, yes, 1 plus 2 plus 3 does equal 6, so this statement is true if we stop at 3. Well, what about if we stop at 4? This statement here is saying that if we stop at 4, then the sum is equal to 4 times 4 plus 1 divided by 2, which is 4 times 5 divided by 2, which is equal to 10. And yes, if we add up these numbers, 1 plus 2 plus 3 plus 4, we do get 10. So it appears that this statement seems to be holding for a couple of values of n. We want to prove that P of n is true for all positive integers. Okay, we could keep trying like we were. So I said, all right, stop at 3, it's true. Okay, stop at 4, it's still true. Okay, stop at 5, I can show that it's true, but I'd be sitting here all day. That's where the notion of mathematical induction comes into play. It's very useful for this. So let me start with step 1 of mathematical induction. Step 1 is to prove that P of n is true for n equals 1, or whatever starting case it is we have here. So we'll prove that that's true by looking at the left-hand side and the right-hand side when n equals 1. Well, the term on the left-hand side when n equals 1 means we start adding the numbers, but we stop right at 1. Okay, so n equals 1 corresponds to the very first term. Then on the right-hand side, we're going to plug 1 in for n. And so that's equal to 1 times 2 divided by 2, or 1. So that we see that the left and the right-hand side of this are equal when n is equal to 1. Therefore, P of n is true for n equals 1. Okay, so we check that off. Okay, step 2 of mathematical induction begins with assuming P of n is true for n equals k. That means that if we sum the first k numbers, it's equal to k times k plus 1 divided by 2. Okay, so we're assuming that this is true, and we need to deduce that P of n is true if n equals k plus 1. Okay, so deduce that this is true, P of n is true for n equals k plus 1, using this as a true statement. So we're going to look at the left-hand side and the right-hand side for k plus 1. So the right-hand side means we add up all the numbers and we stop at k plus 1. Well, now we're going to use this fact here. The sum of the first k numbers is k times k plus 1 over 2. So the sum of all these guys is equal to k times k plus 1 divided by 2. And now we have plus this one extra term. So now let's simplify this. we'll distribute the k's. So we get k squared plus k over 2 plus k plus 1. And now we need to get a common denominator of 2. So we multiply the top and the bottom of this by 2. And then we'll simplify this portion by distributing the 2. So we get k squared plus k over 2 plus 2k plus 2 over 2, and we just combine those into one fraction. So what we end up with is that the left-hand side, when n equals k plus 1, is k squared plus 3k plus 2 all over 2. Now we need to look at the right-hand side, when n is equal to k plus 1. So we go to each n and replace it with k plus 1. So on the right-hand side, we have k plus 1 times k plus 1 plus 1 all over 2. Well, this is equal to k plus 1 times k plus 2 all over 2. And if we multiply this out, we get k squared plus 2k plus k, which is plus 3k, plus 2 all over 2. So therefore we see, since the left-hand side and the right-hand side equal one another when n equals k plus 1, P of n is true for n equals k plus 1. Therefore, by mathematical induction, P of n is true for all positive integers n. Okay, so that's the way mathematical induction works. So again, step 1, we prove that the simplest case is true. Step 2, we assume that the statement is true if we let n equal k. Then we use that to show that P of n is true for n equals k plus 1. Then we're done by mathematical induction. So again, in class, we'll talk about why these steps are sufficient. But hopefully some of you are already thinking about that. Okay, let's see another example. Let P of n be the statement that if you sum these even numbers up to 2 times n, the answer is n squared plus n. So we want to prove that P of n is true for all integers n greater than or equal to 1. So the first step that we have to do is prove that P of n is true for n equals 1. Okay, press pause while you take a look at the left-hand side and right-hand side and show that they're equal. Okay, for n equals 1, the left-hand side is just the first term. The right-hand side we get by plugging 1 in for n. So, since the left-hand side and right-hand side are equal, P of n is true for n equals 1. Okay, for step 2, we're going to assume that P of n is true for n equals k and show that it follows that P of n is true for n equals k plus 1. Okay, so assume that P of n is true for n equals k and deduce that it must also be true for n equals k plus 1. So if P of n is true for n equals k, that means that if we take our sum and end at 2k, it's equal to k squared plus k. Okay, so we're going to assume that this is true, and then we need to show that the left-hand side and right-hand side are equal when n is k plus 1. Why don't you press pause while you work on the left-hand side? Okay, for the left-hand side, we add up all the even numbers until we get to 2 times k plus 1. Now we're going to use this thing here, this statement here that we assume to be true. So the first terms here all add up to k squared plus k. So we get k squared plus k plus 2 times k plus 1. Okay, so we have k squared plus k plus 2k plus 2. So it simplifies to k squared plus 3k plus 2. So the left-hand side is equal to k squared plus 3k plus 2 when n is equal to k plus 1. Okay, now press pause while you work on the right-hand side. Okay, in this step, we have to go to the right-hand side and replace n with k plus 1. So we end up with k plus 1 squared plus k plus 1. So if we multiply that out, we get k squared plus 2k plus 1, then plus this k plus 1. So if we collect like terms here, we have k squared plus 3k plus 2. So we see that the left-hand side and right-hand side are equal when n is equal to k plus 1. Therefore, P of n is indeed true when n equals k plus 1. So, by the principle of mathematical induction, P of n is true for all integers n greater than or equal to 1. Okay, so therefore, by mathematical induction, P of n is true for all integers n greater than or equal to 1.